So we have been discussing about the different types of photoreaction, and we discuss in detail the dipyrmethane rearrangement of 1,4-diene. And if we start with an open chain, we end up with the vinyl cyclopropane as one of the product, and you start with the cyclic system is going to give a bicyclic system through the formation of a three-membered ring. So this radiation has attracted a lot of attention. And then it has been reported earlier that if we have a system like this is a bicyclo 222 cyclo bicyclo 222 octatriene, and then this is nicely set for one pi bond and another pi bond separated by a methylene group, and it is nicely set for a dipyrmethane rearrangement. And it has been found that on direct photolysis and in sensitized photolysis, this gives two different products. Under sensitized photolysis is undergoes dipyrmethane rearrangement, to give so it is going to give is going to is going to attack this one, is going to form a new bond, a generation of a diradical, and of course this radical is already there, and then it forms a double bond once again. And if this bond opens up, because this is a new bond, if you open this, you go back to your starting material, and then we end up with a new diradical through the formation of a double bond, and then this is the new diradical, and then this will combine to give a product like this. This is a three-membered ring. So this is the, and if you write in a proper way, it comes like this: 2 5-membered ring, 1 5, another 5, and 3-membered ring. This is called barrelene. This is a common name for this. Otherwise, it is a bicyclo 222 octatriene, and this is semi-bulvalene. And on direct photolysis, it gives cyclooctatetraene. And this work has been exploited and has been reported to give similar products if we have a benzobarrelene, if we have a dibenzobarrelene. So if we have a benzobarrelene, this is a benzobarrelene, and then if we have a dibenzobarrelene, this is a barrelene, and of course under sensitized condition, HNO, undergoes similar type of rearrangement. This is again nicely set for 2 pi bonds, 1 pi bond, another pi bond separated by methylene group. So any of these, if we can get these 2 pi bonds separated by a methylene group, is also same way. Either way it is so same as this. So both barrelene, benzobarrelene, and dibenzobarrelene undergo similar type of rearrangement to give the corresponding semi-bulvalene. So if we have the product is going to be like this in this case, and then of course a cyclopropane ring, and in this case is going to be dibenzo semi-bulvalene, a 3-membered ring, and then 2 benzene rings on the other side. So not only this, it has also been reported that if we have if we have anthracene, And if we treat it with the dinophile like COC6H5, COC6H5 is a very good dinophile. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. In the 910 anthracene, this bond has been found to be very reactive, and this act as a diene, this part as a diene, and this act as a dinophile. File under thermal condition undergoes 4+2 pi electron system to give of course we have two benzene rings of anthracene, and then this is this 2 benzoyl group COC6H5, COC6H5, COC6H5. So it has been found that just same as this one, this compound also undergo a similar rearrangement under photolytic conditions or sensitized condition. It gives dibenzoyl semi-bilvaline. So involving these double bonds, either these two or these double bonds, we end up with a same as dipymethane rearrangement to give a product like this. Two benzoyl groups here, C6H5, COC6H5, and then this is, so this is the corresponding. So we get a dipymethane rearrangement in simple barrelene, we get a dipymethane rearrangement in benzobarrelene, also get a dipymethane rearrangement under photolytic condition, dibenzobarrelene, to give corresponding semi-bilvaline. And if you have a 2 benzoyl group, also undergo similar type of rearrangement, and so on and so forth. Also there is a possibility of dibenzoyl alkene rearrangement in these cases as well. So we are not going into too much detail of this, but now in addition to this, the anthracene substituted, monosubstituted as well as disubstituted anthracene have also been reported. So if we have a monosubstituted anthracene, here is a R, and then of course we have the same dinophile dibenzoyl acetylene, COC6H5, COC6H5 under thermal condition. They go 4+2 cycloaddition reaction, and as mentioned below, this 9-10 position, they act as a diene to give this same. So we get the corresponding. You have an R here, an H here. Of course, this is H, and then of course 2 benzene rings at this end, and then here as well. 2 benzoyl group COC6H5, COC6H5. So this is this product has been formed. Now what happens when we have a substituted bridge has substituted, and this different substitution have been taken. If we have an R is equal to methyl, methoxy, OH, NO2, CN, and then we also have aldehyde, CHO, we also have CH2OH. Lot of work has been done, and similar adducts have been synthesized, so we can have a similar substituent as well here. And then when it reacts with the substituted 9 substituted anthracene with different substituent like methyl, methoxy, hydroxy, nitro, cyano, aldehydic or CH2OH, and reacts with dibenzoyl acetylene, which is acting as a dinophile, adds to 9-10 position, the diene 4+2 cycloaddition. We have to gives this similar substituted benzobarrelene, dibenzoyl barrelene. Now the question is, what happens when we shine light? Whether we get a similar type of product, what is the fate of these substituents, are where it comes. So let us see the photo product. So if this is the starting material. This is R, is a substituent. This is H here. This is COC6H5. Benzoyl group is a part of acetylene, COC6H5. So, and H nu taking involving these two pi bonds, undergoing dipyrmethane with the methylene group, or involving, so we can expect a new bonding between. You can expect a new bond between this. Is the new bond which is formed, and then we have a diradical here, one radical here, another radical. Oh, sorry. Let's write again. So we have right. This is the new bond which is formed through the attack of this through via the dipyrmethane rearrangement. This is the part of the benzene ring. This is a part of the other benzene ring. This is one radical here, another radical here. Is a two benzoyl group, COC6H5. Another benzoyl group, COC6H5. So these two diradicals now, and there is also possibility that we expect a bonding between these two. So either this, or is also possible to have a bonding like this between these two. So either these two, this bonding, or this bonding. And then if we have a new bonding, then we have a radical here. We have a radical here. Right? Let's write this in a H nu. Is H here. And then we have a two benzoyl group, COC6H5. Here have one benzoyl group, COC6H5. And then we have a radical here. Now this is the first step, either this diradical or this radical, depending upon the involvement of one pi bond and another pi bond. If we can expect a bonding here, or we expect a bonding. If we expect a bonding here, we end up with a diradical here. And of course, we have a substituent R. Is R here, is H here. We have an R here. We have an R here, and we have a H here. Now this will transform to the product. This goes via this aromatization, and then there is a new bond. So if we cleave the new bond, we go back to a starting medium. In order to transform to the product, we break this old bond, and then we end up with a new diradical like this. So this one is a new bond, right? We have it once again. Now it is fully aromatized, and then we have a new radical here. This is already earlier radical. So the benzene ring, this is H here, this is an R here. and the 2 benzoyl group C6H5, COC6H5, 1 benzoyl group COC6H5. Now if we come and combine this, we end up with a product like this. This is also a new bond. So we have a, of course this is not there. Oh, sorry, just redraw again. Right? This is new bond. A new bond is a benzene ring, C6H5. This is the new bond again. Formation of 3-membered ring. We have a benzene ring as well here. And the 2 benzoyl group, COC6H5, COC6H5. And then, now, and there is a substituent R here. There is a H here. Now we can see here the substituent is coming on the cyclopropane ring. If there is a bonding between this. There is also a possibility that there is just a, this attacks here, and then let us see, this gets aromatized, and then it opens up a new bond. Old bond opens up because the new bond, if we go back to starting material, if opens up, we end up with a product like this. So benzoyl group, already aromatized. This is a new, we constructed this, and then we are generating a new radical here, right? And then this is 2 benzoyl group, COC6H5. You get a COC6H5, and then this is R here, this is H here. Now this is going to form a bond here. So this is going to form a 3-membered ring. So we end up with a product like this. Right? Okay. And then we have a bonding this one, and then we have a bonding. So this is a 3-membered ring. This is H here, and then this is R here. This is a phenyl group. This is another phenyl group. This is COC6H5. This is COC6H5. Now, if you see this is the cyclopropane ring which is formed now, and then so there is a competition between the there is a substituent on the cyclopropane ring, or substituent not on the cyclopropane ring, but it is on the 5-membered ring. So it has been found that the product where the cyclopropane ring is on the ring is slightly difficult, and so this route is path A, and this is path. This is also path A, but is only the difference in bonding, because these two double bonds are reacting. So in the one case we are adding this one, and so this seems that this is a more, as far as steric hindrance is concerned, R is not coming on the cyclopropane ring. That's why this is going to be a more stable product and proceeds to the product. Like this, several other examples have been taken by taking a dye substituted substituted systems and so on. So we have also, it has also been found that if we have a di-substituted anthracene R1 and R2 plus COC6H5, this is of course heating, 4 plus 2 cycloaddition reaction. So it has been found that depending upon the bulk of the substitution, how big these anthracenes are, if the anthracene is not playing a major role as far as steric hindrance is concerned, then the 9-10 position is as usual acting as a diene to give the corresponding the adduct like this. COC6H5 is the 2 benzene rings, and then here you have R1, here we have an R2, of course C6H5, COC6H5 here. So we get a corresponding dibenzobarrelene as the adduct with a substituent by where 9-10 is acting as a most reactive diene. So this part is acting as a diene to give this adduct. But if the R and R2 are slightly bigger substituent and there is a hindrance of due to the steric hindrance, this 9-10 dibenzobarrelene 9-10 position anthracene is not acting as a diene, and in that case the terminal ring is acting as a diene to give a naphthobarrelene. So it gives a mixture of two products. COC6H5, and then of course we have a this is called naphthobarrelene, dibenzoyl alkene, naphthobarrelene adduct, and this is dibenzobarrelene adduct. So this type of observation have been found that if R1 and R2 are slightly bulkier, then in that case we are going to get a naphthobarrelene. This diene is not acting due to the steric bigger size and steric hindrance. It may not act as to give it this being a substituent at a bridgehead carbon. On the other hand, the terminal ring, either this or this, is same, acting as a diene to give the naphthobarrelene adduct. Now this, as usual, under photolytic condition, under sensitized condition, gives semi-bulvarine derivative corresponding semi-bulvarine adduct. Now what happens whether the naphthobarrelene also undergo a similar type of adduct or not? So in that case, let us see what happens. It has been found that this also act accordingly. So we have an R1, of course we have a substituent R1 and R2 here, R1 and R2. So we have an R1 and R2. So this naphthobarrelene COC6H5, this is formed when the R1 and R2 substituents are bigger and the 9-10 position of the anthracene is not acting as a diene. On the other hand, this under photolytic condition, as usual, undergo dipyrmethane rearrangement of involving these two double bonds. So we can expect a similar type of adduct. A red diradical here, COC6H5. right? And then it comes back and forms a, and then it opens up to give the corresponding. So we end up with a, right? Of course, we have a, so we get a diradical here is a new bond which is formed. This opens up as this is you have a double bond here. Okay. Right. COC6H5, COC6H5, and then this forms a this radical. This forms a cyclopropane ring. So this forms a corresponding cyclopropane ring, and then we end up with the naphtho-soluble vanillin. This is the this will combine with COC6H5, COC6H5, and then this, and then we have a benzene ring. Naphtho. So this rearrangement has also been reported by different group of workers, especially as I mentioned, Professor George from. Now this is another example, very interesting. The Norrish type, not Norrish type 1, is Norrish type 2. This is a Norrish type 2 reaction. If we have, it has been found that you have a benzoyl group here. And then this is this particular compound is nicely set for you have a H nu. This will and for is alpha, beta, gamma. Is alpha, beta, and gamma hydrogen. There is a possibility of a under photolytic condition. It will carbonyl goes to an excited state. Carbonyl goes to an excited state, C6H5, and then this excited state can abstract gamma hydrogen. A gamma hydrogen abstraction is a type 2 reaction. Gamma hydrogen abstraction of excited carbonyls. So we get a diradical here, and then a radical, an OH here and radical here. Get C6H5. So this radical has been reported to get formed, and now if we write this the same molecule in other way around, is a it is a very interesting rearrangement. It's not the normal type 2 product. If you write this benzene ring, right, and then is this is OH here, and then this gets this undergoes it. There is a involvement of a double bond. There is a involvement of the double bond of the benzene ring to attack. So this goes here, and this attacks on this, and then what we get, we end up with a a product like this, which is really not a normal route for the dipymethane rearrangement, and then we get a product like this, right? So this is goes like this. So we are going to get a 6-membered ring. So let us write 1, 2, 3, 4, 5, and 6. So we are going to get a 6-membered ring here. 1, 2, 3, 4. We are going to get a 6-membered ring here, and then of course there is a double bond here, OH, and there is a benzene ring here. Right? And now this is the enol form. This is, just write 1, 2, 3, 4, and then 5, and then 6. There is the double bond between 4 and 5, and then there is a link between 1 and 6, and then this is enol. This is the enol form, and this will tautomerize to keto form, and then this will get once again fully aromatized. So we end up with a product like this. We'll just write a 6-membered ring, and then of course this becomes ketone, the keto form, and this is a. So this rearrangement of this this is really an interesting rearrangement by type 2 reaction. Type 2 reaction, gamma hydrogen abstraction. Gamma hydrogen abstraction to give the first carbonyl gets excited. Abstraction of a gamma hydrogen to give a 1, 2, 3, 1, 4 diradical. 1, 4, 1, 4 diradical. And then 1, 4 diradical. Since there is a phenyl group, so I have just written the molecule in this way. It's the same thing, and then there is a involvement of 1 pi bond to this, so it gets cyclized to get this enol form and then tautomerized. So it is really an interesting rearrangement drive by type 2 reaction, and so that's all for today. Thank you very much.